One of the obvious weaknesses of the repetitive nearest neighbor algorithm is it is time consuming, and we have to run it a lot of times to get an answer. So it turns out there is a different way of finding a cheap Hamilton circuit, which is much faster. It gets a little different than the nearest neighbor algorithm. It's called the cheapest link algorithm. That's what we're going to get into next. And what's nice about this is you only have to run it one time, and it will typically give us a very good answer. It is also not guaranteed to give us the perfect answer, though, which is a little bit of a pain in the butt. But regardless, let's get into that next. So the cheapest link algorithm. Step one, identify the cheapest link on the entire graph, highlight it. So one of the main differences between nearest neighbor and cheapest link algorithm is that in the cheapest link algorithm, we're going to be examining the entire graph as a whole, and we're trying to link together all of the cheapest edges. We're not going to be traveling from point to point to point, always using nearest neighbor. We're going to be trying to link up every one of the cheapest edges if possible. The reason that this is not perfect also is because following exactly these steps is not. We're going to also kind of box ourselves into a corner in terms of not being able to um, find exactly the perfect solution. Kind of like how in the nearest neighbor algorithm we were sort of forced to use some undesirable edges at the end. Like when we started from A on that previous example, we got a pretty terrible result um, in comparison, right? Because we got a circuit which costed $75 as opposed to 54. Quite a big difference. Um, so the cheapest link algorithm, it's a little bit more of a direct way of finding a really solid answer, also not perfect though. So let's go ahead and practice it, but or let's discuss the algorithm itself for a second. Uh, Identify the cheapest edge on the entire graph, highlight it. Pick the next cheapest link on the entire graph and highlight it. Also, we're not necessarily connecting them in order. We're just looking at the whole graph and connecting that way. So one issue is you're basically going to be highlighting all the cheapest edges of the graph. But the issue is if we just start highlighting all the cheap edges, they're not guaranteed to link up in a way that forms a circuit. So there's two conditions you must remember when running the cheapest link algorithm to make sure that you actually build a Hamilton circuit. Because if you ignore these two things, most likely you're gonna have a bad time. You're gonna run into a problem. So the two criteria that you cannot violate is number one, each vertex cannot have more than two highlighted edges connected to it, which just is a way of saying we have to go into a vertex and out of it. We do not want to have a third highlight within one location. So like in an example, um, where am I? Let's say we have A and we highlight this one and this one. We're not allowed to then highlight B to A. And notice that if I'm trying to do this on the graph creator, it said that that isn't a valid choice. And I'm clicking. You can't see me click, but I'm attempting to click on this one. So anyways, yeah, you're not allowed to highlight more than two edges going into one vertex. The other thing you're not allowed to do is to never close a partial circuit. I mentioned that in the previous video, but that just is, we would, let's go back to the graph creator once again. Like let's say we had selected A and E, and for some reason we wanted to pick edge 19 here. And for some reason the graph creator does not have a problem with this. This is a problem because this would be what's called a partial circuit. Again, the issue here is that we have completed a circuit, but it is not Hamilton, because a Hamilton circuit must hit every vertex, and this does not. So notice that if I try to keep highlighting from there, really I would probably not, if I was to program this, I would not allow that as a choice. But now if I try to select something else, it says that is an invalid choice, and nothing, I'm gonna get stuck. Nothing. I can't do anything. So there's two. Those are the only two things you got to worry about. As long as you don't do those, you will be fine. And let's finish it up. Basically, if or when you run into an edge that violates above, skip it, mark it with an X. Otherwise, continue highlighting the cheapest links until you form a Hamilton circuit. And in this case, I'm going to, instead of using Graph Creator, I'm going to do it by hand because Graph Creator doesn't allow me to X them out and skip over some of them. So let's go back to the whiteboard and try to use the cheapest link algorithm to find a cheap Hamilton circuit here. Okay, so step one is to highlight and also notice it does not matter where I'm starting because the starting location does not matter. With nearest neighbor algorithm, the starting location was very important because it was unique to the answer. But with the cheapest link algorithm, it's always going to be the same answer no matter, there is no start. Uh, so that's one of the obvious main differences. So first step is to highlight the cheapest link on the entire graph, which is 2. So that's number 1. Next step, highlight the next cheapest. Then I'm just going to keep highlighting cheapest, 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 uh, as long as I do not do one of those two things. So next cheapest on the graph is 7, the edge A to D. Edge A to D, next. And also note that I don't have to keep them connected as I'm going. That is not a condition that's not relevant. So that's totally fine choice. They will link up in the end properly, assuming I do not do those two things. Next step is highlight the next cheapest edge, 8. Again, just to review what those two conditions are, because those are paramount to running this properly, is I can't have more than 2 highlighted edges, pretty simple, into a vertex, and I can't close a partial circuit. Also pretty simple, but I just want to be paying attention for those two things as I'm going. So in this case, no partial circuits in my highlights, um, and none of them. B has 2, C has 1, F has 1. Everything has 1 except for B, which is 2. Okay, so next cheapest link on the graph is 9, so that's going to be my next choice. Also, notice that this answer looks somewhat familiar to the answers we were getting from nearest neighbor algorithm. It's using a lot of the same edges because we're picking the cheapest one. So it makes sense that there's a lot of overlap in these methods because they are using the cheapest edges. But they're not necessarily going to give us the same answer. So 9 is next, still no problem. Next up would be 10 for the cheapest edge. Notice that 10, however, I'm going to do a little squiggly, would be a problem because that would close a partial circuit there, B, C, F, which, again, that's one thing that is not allowed. So instead, I'm going to mark that with an X because that edge is not allowed based on condition number 2. So, and we're going to keep going, keep highlighting. I accidentally lost my highlighter down here, so let me rehead that. That was fine. Next up would be 11. Note that 11 is actually going to be totally fine. Because first of all, that would make vertex A have highlighted degree 2, which is cool, and C is 2, which is cool. But also notice that what you might be wondering is it kind of appears as though there's a partial circuit there. But as we discussed in chapter 5, technically that is not a circuit because there is no vertex there. That isn't really a circuit because there is no point. So when looking for partial circuits, it's really easy to visually it can be a little bit confusing, but that is not technically a partial circuit in this context. So let me undo that and then return. So summary, that is totally fine. I have not made a partial circuit. Another way to think about it is if I'm if I'm routing if I'm routing a Hamilton circuit in this case, if I was to go between the different points, I should be able to flow between each one as a unique point in this current circuit. So I could go E, D, A, C, B, F. Notice how it flows very naturally. It forms a circuit, well, minus the completion point. And if we are technically following the cheapest link algorithm here, we're going to keep choosing the cheapest one, but technically we could skip ahead in this problem because I noticed that 5 of my vertices they're all connected together, and the only way to close the circuit would be to link back E and F. But let's follow the algorithm very explicitly and continue to identify the cheap in order of cheapest link, because that's really what we're supposed to do. So after 11 is 12. 12 will not be allowed because that would close a partial circuit. Actually, notice that would also violate condition 1 because it would make B and A both be degree 3, when as highlighted. Notice they now have 3 highlighted edges, so that's not cool in either from either condition. 13 would come next. That should also not be allowed. Notice that that would make D have 3 highlighted edges, no go. Next up would be 15. 15 would make B have 3 highlighted edges. 16 would make C and D have 3 highlighted edges. So notice that all, like, we're really, there's none of these are going to work. The only one that will work is going to be the one that closes the circuit perfectly and completes our Hamilton circuit. And this will give us our answer, which not exactly coincidentally was the same answer we got from before. And now, in order to actually say, well, how do I write my Hamilton circuit? What's my answer? It all depends on where we start. Because again, we're getting a unique circuit as our answer. So let's just say we wanted to start from B or A or whatever. It does not matter. Then we could write out our Hamilton circuit by following along the highlighted edges. Typically, you want to go to the cheaper one first, but it technically does not matter because we're not really using the nearest neighbor algorithm at all, so either answer is fine. So we're going to go B, C, A, D, E, F, B as one way of writing it, or I could do the reverse, B, F, E, A, C, B. And that would be my optimal circuit, which again should have a net weight 54 because it's the same answer we kept getting with the repetitive nearest neighbor algorithm. And we can check just because it's a fresh video. But that would be 2 plus 11 is 13, 7 is 20, 29, 46, plus 8 is 54. Perfect. And we're golden. And that's the cheapest link. In the next video, I'll do another example because this one is notoriously tricky. And I want to give you plenty of examples of the cheapest link.